Okay, I guess we are live now. Perfect. Hello, everyone. Welcome to this week PNS on processing memory. We are getting to the end of the semester. We are going to shift gears a little bit from DRAM to storage. And today here we have Rakesh, which is a PhD here in the Safari Research Group, and he's going to talk a little bit about Flash Cosmos, which is a in-flash book bitwise book bitwise engine for in storage processing. So Rakesh is going to give a little bit of background on how storage works, because we didn't discuss much of that here. Then explain, similar to what we did for DRAM, how we can use those operating principles to do book bitwise operations. So thank you so much, Rakesh, to be here today, and feel free to start when you're ready.
Thanks, Gerardo. Thank you for this opportunity. So today I'll be discussing how we can enable bulk bitwise operations within the flash chips so that we can further reduce the data movement and also improve the performance and energy efficiency. So this work was published at Micro 2022, and I'll start with an executive summary. So the background for this work is that bulk bitwise operations are widely used in many important data-intensive applications like databases, graph processing, cryptography. And when we look at the current approaches of performing bulk bitwise operations, we see that there's a lot of data movement between the storage and the compute units in traditional systems and in storage processing, which reduces the performance and energy efficiency. And if we look at prior in-flash processing techniques, we see that it performs a lot of data sensing or serial reading of operands, which also reduces the performance. And we also looked at the reliability aspect in prior in-flash processing techniques, and these approaches provide very low reliability or expect the applications to be tolerant for errors during computation. So the goal of this work is to improve performance, energy efficiency, and reliability of bulk bitwise operations with in-flash processing. So the key idea is we propose Flash Cosmos, which is flash computation with one-shot multi-operand sensing. It's an in-flash processing technique that is based on two key ideas. We propose multi-word line sensing, which enables multi-operand bulk bitwise operations within a single sensing read operation. And we also propose an enhanced SLC mode programming, which increases the voltage margin between the erased and the programmed states to provide high reliability during in-flash computation. So some key results of this work. So we evaluated Flash Cosmos on 160 DL3D NAND flash chips, and we did a system level evaluation with state-of-the-art SSD simulator on 3 real-world applications. And we observed that Flash Cosmos improves the performance and energy efficiency by 3.5 times and 3.3 times over the state-of-the-art IFP technique while providing high reliability during computation. Now, this is the outline of my talk. I'll start with the motivation for this work, then go to the background and then the key idea, and wrap it up with some evaluation results. So bulk bitwise operations are widely used in many important applications. We list some of these applications here: databases, web search, genome analysis, cryptography. So it's widely used everywhere. So the key problem here is that we tend to perform these bulk bitwise operations in the host CPU when the data is stored in the storage units or in the main memory. So the data movement between the compute units and the main memory and the memory hierarchy significantly affects the performance of these operations. So let's look at what this data movement bottleneck is. So in conventional systems, as I mentioned, we call it outside storage processing. The data is moved from the storage system to the host CPU through the memory hierarchy. So here we look at a simple cartoonish figure of the host processor, which could be either a CPU or a GPU, then the main memory and the storage. storage device, which is typically an SSD. So we see that the data is read from the storage to the main memory, and then from the main memory to the host processor through these memory through these interconnects, and then when the computation is performed, we write the data back to the main memory and back to the storage. So here we see that the bandwidth, the external I/O bandwidth of the storage device, typically the PCIe bandwidth, is around 8 gigabytes per second compared to the memory bandwidth, which is tens to hundreds of gigabytes per second. So this is the major bottleneck in data movement, and this is the key bottleneck for performing these bulk bitwise operations in the host processor. Now we look at near data processing techniques, and this paradigm is to move the computation closer to where the data resides. And we observe that there are a lot of there are some prior works which propose techniques to perform computation close in at various levels of memory hierarchy. So in at the cache hierarchy, you have compute cache, and the DRAM you have Ambit and P2O for NVMe based main memory, and then we have Biscuit for storage and in-flash Parabit for in-flash processing. Our key focus is on these two aspects, the in-flash and in-storage techniques, because the data set that we have doesn't fit into the main memory. So it has to come from the storage. So let's look at in-storage processing and how it performs bulk bitwise operations. So in-storage processing performs these computations on an in-storage compute unit, which is typically an embedded core or FPGA. And this reduces the external data movement by transferring only the computation results to the host. Now let's look at this example again and see how the computation is performed. So we have a more granular representation of a storage device here, because we want to show the in-storage compute unit along with the NAND flash chips where the data resides. So so the data is read from the NAND flash chips to the in-storage compute unit, and here the computation is performed, which is typically the bulk bitwise operations, and then the result goes outside the storage device to the host CPU or the GPU. So if we look at the bottleneck here, we see that the internal I/O bandwidth of the storage device, which is not very high compared to the external I/O bandwidth, is the key bottleneck here, and that remains a challenge for performing bulk bitwise operations in storage within the storage device. So the internal I/O bandwidth is the main bottleneck. Now we further move the computation closer to where the data resides, which is to the flash chips. And in-flash processing performs computations within the flash chips as the data operands are being read serially. So IFP further reduces the internal data movement bottleneck in storage by transferring only the computation results to the in-storage compute unit. So here we again look at this figure, and the computation is performed within the flash chips. We'll show how this is done in the next slide. And the result is moved through to the SSD, the in-storage compute unit, and then the result is transferred outside the storage device through the memory hierarchy. So the key bottleneck here in this in flash processing techniques is the serial data sensing. So as we know that within the in a storage device, the read operations are quite expensive, and these prior techniques try to perform serial sensing of data or the operands, which results in reduced performance. So let's look at what this data sensing bottleneck in IFP is in a bit more detail. So the state-of-the-art IFP technique performs bulk bitwise operations by controlling the latching circuit of the page buffer. So here we see a more granular figure representation of the flash chips. So you can see that a flash chip contains several number of pages and a page buffer, which is an intermediate buffer to move the data from the pages to the in storage compute unit or vice versa. So uh, let's assume that there are the operands are stored in these flash pages, and if we need to perform these computation, if we need to perform in flash processing, we need to read the data in a serial manner. And as you can see, if we read the data one by one, then we get the result of two operands. And if we again read another operand, then we get the bitwise AND of three operands. So this is so the serial data sensing is the bottleneck in in-flash processing techniques. Now there is another aspect that affects the in-flash processing techniques, which is the reliability. So as we know, NAND flash memory is a highly error-prone substrate, and this is because of many sources of disturbances. So typically, manufacturers use error correction codes and data randomization techniques to mitigate these errors. However, because in-flash processing techniques perform computation within the flash chips, we cannot leverage these mitigation techniques like ECC and data randomization because these mitigation techniques are residing in the SSD controller. So here you can see that the data is, let me just, okay. So here you can see that the flash chips are connected to the SSD controller through channels, and the data resides within the flash chips. And whenever the data is read from the flash chip, it goes through the ECC engine and the randomization module within the SSD controller to basically mitigate the errors. But this also results in a lot of data movement if we have to keep moving the data through the channels to perform error correction. So if prior approaches suffer from these erroneous computation results due to high raw-bit error rate of NAND flash memory. So as you can see here, if there are errors in the operands, then when we perform the serial sensing of data, these operands remain in the computation result or even get compounded at some point. So prior IFP techniques require the application to be highly error tolerant. So our goal here is to address the bottleneck of the state-of-the-art IFP techniques, which is the serial sensing of operands, and also make IFP more reliable by providing accurate computation results. So our proposal is Flash Cosmos. As I mentioned earlier, we perform computation on multiple operands using a single sensing operation. We show the same figure of a flash chip with multiple pages where the operands are stored, and we have a page buffer. So when we perform a single sensing operation of all the operands within the flash chip, and we get the result at one shot in the page buffer. And we also use techniques to make the computation result very highly reliable. And this is the proposal that we are going to discuss more in the next slides. So before I jump to the background, if there are any questions on YouTube, I would like to answer that. Okay, there are no questions so far. So let me move to the background. So we'll start with some background on the simplest unit of a of an SSD, which is the flash cell. So a flash cell stores data by adjusting the amount of charge in the flash cell. So if there is very low charge, then it's an erase cell, and the data, and it represents the value 1. And if it's having very high charge level, then it's a programmed cell, and the value it represents is 0. So when we activate these cells, or when we read these cells, if it's a erase cell, then it operates as a resistor, and if it's a programmed cell, then it operates as an open switch. So let's look at how these flash cells are connected within the SSD. And we have a unit called the NAND string, where a set of flash cells are connected serially to form the NAND string. And this NAND string is connected to a bit line. So when we want to perform a read on these flash cells, let's say we want to read one of the flash cells within the NAND string. The other flash cells which are connected to the NAND string operate as non-target cells, regardless of the stored data. This is because of the high pass-through voltage that we supply to these non-target cells. And when we activate these the target cell, it either operates as a resistor or an open switch based on the state of the cell. And when we perform the read, the bit line current flows through the NAND string. And if the cell operates as a resistor, then the bit line current is able to pass through the NAND string, and the sense amplifier reads the value as 1. And if there is an open switch, if the target cell is programmed and it acts as an open switch, then when the bit line current passes through the NAND string, it blocks the bit line current, and the sense amplifier reads it as a value 0. So this is a simple explanation of how the read operation works. And now let's move on to more higher level abstraction, which is a NAND flash block, where we have a number of NAND flash strings which are laid out in next to each other, which are connected to different bit lines. But the cells at the same level of this, at the same level across different NAND flash strings are connected to form a word line. So these word lines control a large number of flash cells, and it also provides high bit level parallelism. Now, when we move much higher in the abstraction, we see that there are a large number of these blocks which share the same bit lines. And you can see there can be thousands of blocks which have NAND strings within them, and which share the same bit line, as we show here. So one takeaway that we see here is that the cells in the same block are connected serially, and this is similar to the digital AND logic. We show a 2-input AND logic here, which is where the transistors are connected in series. And if we look at the cells that are connected in across different blocks, but when they share the same bit line, it is similar to the digital OR logic that we learned in our previous courses. So here we see that these transistors are connected in parallel. So with this understanding, we'll jump to Flash Cosmos, the key idea of Flash Cosmos, and how we enable a reliable computation within the flash chips. See, there are no questions on YouTube, so I'll move on to the key mechanism. So Flash Cosmos has two components in it. One is the multi-word line sensing, which enables in-flash bulk bitwise operations on multiple operands with a single sensing operation. So let's jump to that. So we have two types of multi-word line sensing operations based on the key insights that we saw in the background. we have bitwise AND, which or intra-block MWS, which simultaneously activates multiple word lines in the same block, and this results in the bitwise AND of the stored data in the word lines. So here we see a single block where we have multiple word lines which are connected, which connect cells from different NAND strings, and so here we, let's say we want to read two word lines within the block simultaneously. Based on the state of the cell, whether it either operates as a resistor or an open switch. And when we read all these bit lines simultaneously, or send the current through these bit lines simultaneously, based on the value of this cell, if it acts as an open switch, then the current doesn't pass through the bit NAND string, and the result is zero. But if there is a NAND string where all the cells operate as resistors, then the value is one. So as I mentioned, the value is one if all cells store the value one, and this is equivalent to a bitwise AND of the target cells. Now, even if there is a single cell which operates as an open switch, the current doesn't pass through the NAND string, and then we see the result as zero. So this means that this is equivalent to the bitwise AND of all target cells, and if there is a target cell which stores zero, then the result will, even if there's one target cell which stores the value zero, then the bit line current is, the end result is going to be a zero. So intra-block MWS enables bitwise AND of multiple pages in the same block with a single sensing operation. Now, there is another multi-word line sensing technique, which is inter-block MWS, where we read word lines across different blocks. And we currently support reading up to 4 word lines across 4 blocks, let's say. And we simultaneously activate these 4 multiple word lines in different blocks. And this results in the bitwise OR of the stored data in the word lines. So here we show an example where there are 2 word lines. And again, when we read these word lines simultaneously, the bit line current passes through these NAND strings. And since the NAND strings are connected in parallel here, so you can see that even if when both the cells operate as resistors, the value will be 1. But even if one of the cells operate as an open switch, the value would still be 1 because they are connected in parallel, and because the current flows through the other NAND string, and the result would be read as 1. So this is similar to the OR logic, and so the result will only be a 0 when both the cells store the value 0. So here we show an example with 3 word lines, but the principle remains the same here. So inter-block MWS enables bitwise OR of multiple pages in different blocks with a single sensing operation. So now that we have seen bitwise AND and bitwise OR, we also support other bitwise operations in Flash Cosmos. We propose bitwise NOT, and how do we do that is by exploiting inverse read operation, which is already supported in the modern NAND flash memory for copy back operations. We show how we can perform bitwise NAND and NOR, and this is using bitwise AND and OR, but also using inverse read operations simultaneously. And we also show how we can perform bitwise XOR or XNOR between the latches that are present in the flash memory. So these operations are already supported. So we can leverage these operations to perform more complex bitwise operations. Now, we've seen how we can perform a single sensing operation to either perform bitwise AND or bitwise OR. Now we'll move on to how we can make these operations more reliable. And we propose enhanced SLC mode programming, which increases the reliability of in-flash bulk bitwise operations. So let's jump to ESP. So enhanced SLC mode programming is a technique where, so typically we in the SLC mode programming, there is a large voltage margin between the erased and the programmed states. So you can see a simple voltage distribution of a SLC flash cell or a flash word line. So you have some cells which are in the array state, some cells in the programmed state, and the threshold voltage is in the x-axis, and you have a number of cells in the y-axis. So you have a large enough voltage margin between the two states. So even when there is a disturbance, some cells can shift from the array state to towards the program state, or in the reverse direction, but it still holds well if because of the large voltage margin. But we observe that SLC mode programming cannot still enable error-free computation, because in flash processing techniques we cannot use ECC and data randomization. So so how do we mitigate this? So what we propose is, in ESP we further increase the voltage margin between the erased and the programmed states, and this wider voltage margin. So you can see that the newer programmed state is much farther from the array state with the increased voltage margin, and this wider voltage margin makes the improves the reliability by making the cells less vulnerable to errors. And this is achieved by performing additional steps in the incremental step pulse programming technique, which is the typical programming technique used in modern NAND flash memory. And this increases the voltage margin. So ESP improves the reliability of in-flash computation without the use of ECC or data randomization techniques. And this technique can, in fact, improve the reliability of prior approaches as well. So now that we have seen the two techniques of Flash Cosmos, the next step is to look at how we enable these techniques from the point of an SSD, or when we look at how we can use these techniques from the SSD or from the host. So Flash Cosmos supports 3 new commands. So we have an MWS command, which is used for performing this single sensing operation of multiple word lines. We have an enhanced SLC mode programming command, which enables reliable data computation. And then we have an XOR command, which is used for performing XOR operation between 2 operands. So if you look at MWS command, it actually supports intra and inter-block MWS. It supports inverse read operation, and it also enables accumulation of all results from different reads. And then we have a flag or a bunch, an ISCM command, which allows the flash controller to turn on or off 4 features. One is the inverse read mode, which is represented by I. The sensing latch initialization. So there are 2 latches within the flash chips, a sensing latch and a cache latch. So if we have to initialize both these latches, then we use the set a flag for the 2 latches in the ISCM command. And then if we have to move data from S latch to C latch, then we have another flag which enables this data movement. Now, we also provide the address slot within this command. So there is each slot in this provides the SSD controller to set the block addresses from which we read this from which we perform the MWS operations, and also the page bitmap, which enables the which provides the bitmap for setting the different word lines which needs to be sensed simultaneously. So we provide 4 different address slots for interblock MWS command. And ESP command works very similar to the regular program command, and the XOR command performs bitwise OR between the sensing and the cache latches and stores the result in the cache latch. Now, let's look at a simple operational example. Here we see an equation which is performing bitwise AND and bitwise OR of multiple operands. So how do we achieve this with Flash Cosmos? So let's look at it in a bit more detail. So we first look at the second half of the equation where we see um, a bitwise OR performed on 2 operands, C1 and C3, and and D2 and D4, and then we perform the bitwise AND on the result of these 2 operations. So here in the first step we see that, and what we try to do here is we basically convert this part of the equation into bitwise, more of bitwise AND operations, because we from our characterization we observe that bitwise OR operations consume more power than the bitwise AND operations. So we store the operands C and D in different blocks, and we store the negated value of these, or we use the inverse read operation for these operands to basically convert them to bitwise AND operations instead of bitwise OR. And then we finally perform the inverse of the entire operation. So here you can see that we set the block number and the word lines where from which the data has to be sensed in these in the block and the page bitmap. And since there are 2 operations happening simultaneously across different blocks, we have another slot for reading the block D. So we also support that in the MWS operation. And we set the flag to I, because this is the first operation we perform. We set the initialization of sensing and the cache latches by setting those flags, and we also set the movement between the sensing and the cache latch. And because we are performing the inverse read operation, we set that flag as well. So so we issue a command to achieve this. And in the next step, what we do is we look at the first half of the equation where we see a bulk bitwise AND operation of 4 operands, and along with a NOR operation of A1. So we similarly again set these block and page bitmaps of these in the MWS command. But this is since this is a continuation of with the previous operation, we don't set the sensing and the cache latch initialization here. So that's and we are not performing inverse read operation in this case, so we don't set that as well. So like this we can actually realize a large bitwise operation through using MWS commands. So that's in a very short. That's a very short introduction to the mechanism of Flash Cosmos. We have a lot more details in our paper, which I'm going to show which I'm going to provide the link for in a few more slides. But yeah, this is the key idea of Flash Cosmos. So if there are, see if there are questions on YouTube. Okay, there are no questions, so we'll move on to the evaluation. So, so we evaluate Flash Cosmos using two approaches. We see the feasibility of performing the MWS operations and enhanced SLC mode programming using 160 real state-of-the-art 3D NAND flash chips. So this device characterization involves validating the feasibility, performance, and reliability of Flash Cosmos. We do it on 160 48 layer 3D TLC NAND flash chips. We test around more than 3.5 million word lines, and under worst case operating conditions, where we subject them to 1 year retention time at 10,000 P cycles, and also program them with worst case data patterns. So the results of the real device characterization shows that both intra and interblock MWS operations require no changes to the cell array of commodity NAND flash chips. These can be achieved in commodity flash chips without much changes. And both MWS operations can activate multiple word lines, as we see in our in the flash chips that we have used. We can perform up to 48 intra block MWS we can read up to 48 word lines within the same block, and we can read up to 4 word lines across different blocks at the same time. And this only comes at a small increase in sensing latency of less than 10%. And the enhanced SLC mode programming significantly improves the reliability of computation results, and we see 0-bit errors in the tested flash cells. Now, the other way we evaluate Flash Cosmos is using a system level evaluation with 3 real world applications that perform these bulk bitwise operations. So for this system level evaluation, we use MQSIM, which is the state of the art SSD simulator. And we use this simulator to model the performance of Flash Cosmos and also the baselines. And the workloads we use for this evaluation, we use 3 of them. Bitmap indices, which performs bitwise AND of up to 1,000 operands. Then we have image segmentation, which is an image processing kernel, which performs bitwise AND of 3 operands, but these operands are very large, up to 44 gigabytes each operand. And then K-clique star listing, which is a graph processing kernel, which performs bitwise OR of up to 32 operands. Now, the baselines that we model for this system level evaluation is the outside storage processing, which is the typical host centric computation. We model the multi-core CPU, which performs these computations. And we model the in-storage processing architecture, which is using an in-storage hardware accelerator, like an ARM core. And we also model Parabit, which is the prior in-flash processing mechanism, which performs serial sensing of operands. Now, the results show that we show both performance and energy efficiency results for these 3 operations. And in both cases, we normalize the performance and energy efficiency to the performance of the outside storage processing. And we show the average results for each workload. So here we see that, on average, we see that Flash Cosmos provides up to 3.5 times the performance of Parabit, and or it shows an increase in performance by 3.5 times. And energy efficiency wise, we see an increase of 3.3 times energy efficiency compared to the prior in-flash processing techniques. And Flash Cosmos provides significant performance and energy benefits over all the baselines, as you can see here. And these performance and energy efficiency benefits only increase if there are more operands. So if we can perform more multi-word line sensing and read more operands at the same time, then we see the benefits increase much more. So we have a lot more of characterization and results in the paper, and this is the link to the archive version of this work. So I would encourage everyone to take a look and let us know your comments or feedback about this. So I'll move to the summary quickly. So Flash Cosmos is the first work to enable multi-operand bulk bitwise operations with a single sensing operation and high reliability. Flash Cosmos improves performance by 3.5 times over the prior in-flash processing technique. It increases energy efficiency by 3.3 times over the prior approach. And all these changes come at a very low cost and require no changes to the flash cell arrays. And with that, my presentation ends. And if there are any questions, I'll be happy to answer them.
Rakesh, thank you so much. We don't have any questions on YouTube, but I have one question. So what is next for Flash Cosmos?
Yeah, that's a very good question, Geraldo. So we are actively looking at this direction, and as we saw in one of the slides, we can perform more complex bulk bitwise operations, but we are looking at how we can enable more complex computation like addition, multiplication, and even more. And there are a lot more possibilities that we can look at. So that's the next step in this direction, to be sure.
Yeah, that's really exciting actually. And so I guess there are no more questions on YouTube. Thank you once again, Rakesh, for discussing Flash Cosmos today. And next week should be our last PNS class. We're going to discuss what are the challenges of enabling data-centric computing in current systems. So stay tuned for that. And once again, thanks so much, Rakesh, and have a good day, everyone.
Thank you, and have a nice day.
Bye-bye.